Welcome! In this session, we'll dive into the problem number 684, redundant connection. This problem is a fascinating challenge where we aim to identify and remove an edge in a graph to ensure it becomes a tree. Let's explore the approaches, insights, and techniques to solve this problem effectively. Stay tuned! Here, we are tasked with finding a redundant connection in a graph. The graph starts as a tree with nodes labeled from 1 to n. Then, one additional edge is added, and that extra edge creates a cycle in the graph. Our goal is to write a function that identifies and removes the edge responsible for the cycle, ensuring that the resulting graph becomes a valid tree once again. If there are multiple edges that could be removed, we need to return the one that appears last in the input list of edges. The input consists of a list of edges, where each edge is represented as a pair of integers, u, v, connecting two nodes. The output is a single edge, also a pair, u, v, which represents the redundant connection. To understand the problem better, let's look at an example. For the input edges equals 1, 2, 1, 3, 2, 3, the output is 2, 3. Here's why: the graph initially forms a tree with the edges 1, 2, and 1, 3. However, adding the edge 2, 3 creates a cycle involving the nodes 1, 2, and 3. By removing this edge, the graph reverts to a valid tree structure. In another example, with edges equals 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 1, 3, the output is 1, 3. Here, the first cycle occurs when the edge 5, 1 is added, but the edge 1, 3 creates another cycle later in the input. Since 1, 3 appears last, it is the redundant edge to remove. Now, let's consider the constraints in edge cases. The graph will always have between 3 and 1000 nodes, and it is guaranteed to contain exactly one cycle. Each edge in the input connects two distinct nodes, meaning u is not equal to v, and there are no duplicate edges. Importantly, the graph is connected, ensuring that all nodes belong to a single component. When dealing with edge cases, we need to handle scenarios where the graph has the minimum number of nodes, such as 3 nodes forming a cycle, or where the redundant edge appears at the very end of the input list. Additionally, the redundant edge might connect nodes that are far apart in the graph, so our solution must efficiently detect and resolve these cases. To address this problem, one straightforward approach we can consider is the brute force method, which involves checking for cycles by temporarily removing edges. The intuition here is that a graph without cycles is a tree, so removing the redundant edge should eliminate the cycle and result in a valid tree. The process involves iterating through each edge, removing it, and then performing a graph traversal, such as DFS or BFS, to ensure the graph remains connected and acyclic. If the graph meets these criteria, the removed edge is identified as redundant. However, this approach is computationally expensive because for each edge, we must traverse the entire graph. This results in a time complexity of O(n squared, where n is the number of edges. Additionally, we require O(n) space for the graph structure and recursion stack. While conceptually simple, this method becomes impractical for larger graphs due to its inefficiency. This inefficiency highlights some key drawbacks of the brute force approach. It requires repeated graph traversals, making it unsuitable for large inputs. Furthermore, it does not take advantage of the problem's structure to optimize the solution. To address these issues, we turn to a more efficient method, the union-find algorithm, also known as disjoint set union. The core intuition behind this approach is that adding an extra edge to a tree creates a cycle, and the redundant edge is the one that connects two nodes already in the same connected component. Union-find is particularly well suited for this problem because it efficiently tracks connected components and detects cycles. If, while processing an edge, we find that the two nodes it connects already belong to the same component, that edge must be redundant. This method directly leverages the structure of the problem, offering a much more efficient solution. To implement the union-find approach, we start by initializing a union-find structure for the graph's nodes. Then, we iterate through each edge, processing them one by one. For each edge connecting nodes u and v, we first check if these nodes belong to the same connected component using the find operation. If they do, this means adding the edge creates a cycle, and we return it as the redundant edge. If not, we unify the two components using the union operation. The process continues until we identify the redundant edge. This approach is highly efficient, with a time complexity of O n asterisk alpha n, where alpha n is the inverse Ackermann function, which grows extremely slowly and is almost constant for practical purposes. The space complexity is O n, used for the parent and rank arrays. This optimized solution is not only efficient but avoids the need to explicitly construct the graph, making it a direct and elegant approach to solving the problem. Given the efficiency and alignment with the problem structure, we chose the union find algorithm as our strategy. While the brute force approach is simpler to understand, it has a prohibitive time complexity of O n squared, making it impractical for larger graphs. In contrast, union find offers near constant time operations, making it optimal for this problem. The key insight, or aha moment, was realizing that detecting a cycle could be reduced to checking whether two nodes belong to the same connected component. This insight, combined with the dynamic connectivity capabilities of union find, provides a robust and scalable solution. While union find does require some additional understanding and effort to implement, the trade-off is well worth it given its performance advantages. For problems involving dynamic connectivity or cycle detection, union find stands out as the go-to solution, making it the most suitable choice for addressing the redundant connection problem. In this problem, we need to find the redundant edge in a graph that causes a cycle. Initially, the graph is a tree, which means it's connected and acyclic, but one additional edge has been added, creating a cycle. Our goal is to identify and remove this extra edge so that the graph is restored to a tree structure. One way to solve this is through a brute force approach. First, we take the input graph represented as an edge list, where each edge connects two nodes, u, v. The graph has n plus 1 edges for n nodes, which means one edge is unnecessary. We iterate over all the edges and temporarily remove each edge one by one. By simulating the removal of an edge, we create a new graph representation that excludes the current edge. This allows us to evaluate whether the removal breaks the cycle or disrupts the tree structure. After removing an edge, the next step is to determine whether the resulting graph is still a valid tree. For this, we need to check two properties. First, the graph must be acyclic, there should be no cycles remaining. Second, it must be connected, meaning all nodes are reachable from any starting node. To verify these properties, we can use a graph traversal algorithm like depth-first search, DFS, or breadth-first search, BFS. If the graph fails either the acyclic or connected condition, it means removing this edge did not resolve the issue, so we restore the edge and move to the next one. However, if removing the edge makes the graph a valid tree, then that edge is the redundant one. Finally, we return the first edge that creates a valid tree when removed, which satisfies the problem's requirements. The key to solving this problem lies in understanding tree properties. A tree with n nodes always has exactly n1 edges. Adding one extra edge introduces a cycle, and removing this edge restores the tree structure. While the brute force approach is straightforward to implement, it is not efficient, with a time complexity of O, e asterisk, v plus e, where e is the number of edges and v is the number of vertices. However, this method works well for small graphs. Detecting cycles is critical in this approach, and graph traversal techniques like DFS or BFS can efficiently identify cycles. To support the algorithm, we use an edge list to represent the graph, which allows for easy manipulation of edges, and a visited set to track nodes during traversal, ensuring we don't perform redundant checks. The brute force approach has some notable complexity characteristics. The time complexity is O, e asterisk, v plus e, as for each edge we remove, we perform a graph traversal. The space complexity is O, v plus e, which accounts for storing the graph and the visited nodes during traversal. There are also several edge cases to consider. First, if removing an edge causes the graph to become disconnected, that edge cannot be the redundant one. Second, the algorithm assumes there is only one cycle, as guaranteed by the problem constraints. If there were multiple cycles, the approach would not work as intended. Finally, self-loops edges that connect a node to itself are not valid in a tree structure and can be directly identified as redundant without additional checks. To solidify our understanding, let's walk through an example. Consider the input edges 1, 2, 1, 3, 2, 3. We begin by testing the removal of the first edge, 1, 2. The remaining edges are 1, 3, 2, 3. Checking the graph, we see it remains connected and acyclic, so we move on. Next, we remove edge 1, 3. The remaining edges are 1, 2, 2, 3. Again, the graph is connected and acyclic, so we continue. Finally, we remove edge 2, 3. The remaining edges are 1, 2, 1, 3. This time, the graph is connected and acyclic, and removing the edge resolves the cycle. Therefore, the redundant edge is 2, 3, which we return as the output. Here, we begin by defining the findRedundant connection method inside the solution class. This method takes a list of edges as input. To implement the solution, we utilize the union find algorithm. First, we define a helper function called find, which is responsible for finding the root of a given node. This function uses path compression to optimize the process, ensuring that nodes point directly to their root, reducing the depth of the tree and speeding up future operations. Next, we define another helper function called union. This function takes two nodes as input and attempts to unite their sets. It first finds the roots of both nodes, and if the roots differ, it merges the smaller tree into the larger one based on their rank. If the ranks are equal, we arbitrarily choose one tree to become the root and increase its rank. The union function returns true if the nodes were successfully united, and false if they were already connected. Finally, we initialize the parent array, where each node starts as its own parent, and its size is determined by the number of edges plus 1 to account for 1-based indexing. We also initialize the rank array with zeros for all nodes, which helps us track the tree depth. Now, we iterate through each edge in the edges list. For every edge, we extract the two nodes it connects. Using the union function, we attempt to unite these nodes. If the union function returns false, it means the edge forms a cycle because the nodes are already connected. In this case, we immediately return the current edge as the redundant connection. This approach ensures that we identify the first edge that closes a cycle, adhering to the problem's requirements. The algorithm operates efficiently, with the union find operations being nearly constant time due to path compression and rank optimization. Here, we start implementing the solution in Java by defining the solution class and the findRedundant connection method. The input is a 2D array of edges, where each edge connects two nodes in the graph. To handle the union find approach, we initialize two arrays, parent and rank. The parent array keeps track of the representative node for each set, while the rank array helps optimize the union operation by keeping the tree as flat as possible. Initially, every node is its own parent, and the rank of each node is set to 0. Next, we define a helper method find. This method uses path compression to efficiently find the root or representative of a given node. If the node's parent is not itself, the method recursively updates the parent to point directly to the root, ensuring faster lookups in future operations. Lastly, we start defining the union method, which will attempt to merge two sets by combining their roots. If the two nodes are already in the same set, the method will return false, indicating a cycle. Now, looking deeper into the union method, we compare the ranks of the two roots to decide how to merge the sets. If the rank of the first root is greater, the second root's parent is updated to point to the first root. Conversely, if the second root has a higher rank, the first root's parent is updated to the second root. If both roots have the same rank, we arbitrarily choose one as the new parent and increment its rank to reflect the increase in tree height. This ensures the union operation remains efficient. After defining the helper methods, we process each edge in the graph. For each edge, we extract the two nodes it connects and attempt to unite their sets using the union method. If the union operation returns false, it means the two nodes are already in the same set, and the current edge creates a cycle. Thus, we immediately return this edge as the redundant connection. Finally, if the input is valid, the loop should always find a redundant edge, so the return statement at the end is just a safeguard and should not be reached during normal execution. To solve the problem, we'll use the union find algorithm. Let's start with a simple example where the input edges are 1, 2, 1, 3, 2, 3. Initially, each node is its own parent, and all ranks are set to 0. This means our parent array is 0, 1, 2, 3, and rank is 0, 0, 0, 0. Now, we process the edges one by one. For the first edge, 1, 2, we find the roots of nodes 1 and 2. Since neither is connected yet, their roots are themselves 1 and 2. These are different, so we perform a union operation. Node 2's parent becomes 1, and we increment the rank of node 1. Our updated state is parent equals 0, 1, 1, 3, and rank equals 0, 1, 0, 0. Next, we process edge 1, 3. Again, we find the roots of nodes 1 and 3, which are 1 and 3 respectively. Since the roots differ, we perform another union. Node 3's parent becomes 1. The updated state is now parent equals 0, 1, 1, 1, and rank equals 0, 1, 0, 0. The next edge is 2, 3. When we find the root of node 2, it points to 1 due to path compression. Similarly, node 3's root is also 1. Since both nodes share the same root, adding this edge would create a cycle. Therefore, we return 2, 3 as the redundant connection. Now, let's look at another example with a larger graph where edges are 1, 2, 2, 3, 3, 4, 1, 4, 1, 5. We initialize the parent array as 0, 1, 2, 3, 4, 5, and the rank array as 0, 0, 0, 0, 0, 0. Processing the first edge, 1, 2, we find the roots of nodes 1 and 2 to be 1 and 2. Since the roots are different, we union them. Node 2's parent becomes 1, and we update the rank of node 1. The parent array becomes 0, 1, 1, 3, 4, 5, and the rank array is 0, 1, 0, 0, 0, 0. Next, we process edge 2, 3. The root of node 2 is 1, and the root of node 3 is 3. Since the roots differ, we perform a union. Node 3's parent is set to 1. The updated state is parent equals 0, 1, 1, 1, 4, 5, and rank equals 0, 1, 0, 0, 0, 0. For edge 3, 4, we find the roots of nodes 3 and 4. Node 3's root is 1, and node 4's root is 4. Again, the roots differ, so we union them. Node 4's parent becomes 1. The parent array is updated to 0, 1, 1, 1, 1, 5, and rank remains 0, 1, 0, 0, 0, 0. Now, processing edge 1, 4, we find that both nodes 1 and 4 have the same root, which is 1. This indicates a cycle, so we return 1, 4 as the redundant connection. In this example, we explore a smaller edge case where the graph contains sequential connections with edges 1, 2, 2, 3, 3, 1. Initially, we set up the parent array as 0, 1, 2, 3, and rank as 0, 0, 0, 0. Starting with edge 1, 2, we find the roots of nodes 1 and 2, which are 1 and 2 respectively. Since they are different, we perform a union. Node 2's parent becomes 1, and we increment the rank of node 1. The updated state is parent equals 0, 1, 1, 3, and rank equals 0, 1, 0, 0. For edge 2, 3, we find the root of node 2, which is 1 through path compression, and the root of node 3 is 3. Since the roots are different, we union them. Node 3's parent is set to 1. The parent array becomes 0, 1, 1, 1, and rank remains 0, 1, 0, 0. Finally, we process edge 3, 1. The root of node 3 is 1, and the root of node 1 is also 1. Since they share the same root, adding this edge would create a cycle. Thus, we return 3, 1 as the redundant connection. This concludes our exploration of this example, demonstrating how the union-find algorithm efficiently identifies cycles in graphs by managing parent and rank arrays. To analyze the time complexity of our solution, we start with the initialization of the union-find data structure. This involves creating two arrays, the parent array, which keeps track of the parent node for each element, and the rank array, which helps manage the depth of the trees to optimize union operations. Both arrays have n+1 elements, accounting for all nodes from 1 to n, inclusive. Initializing these arrays requires assigning values to each of their n+1 positions, making the total time for this step O(n). This initialization is essential for the algorithm to function efficiently. Now, when processing each edge in the graph, the algorithm uses the find function to determine whether the two nodes connected by the edge belong to the same connected component. The find function incorporates path compression, which flattens the structure of the tree over time, ensuring that the amortized time complexity of each find operation is O, alpha, n. Here, alpha, n, is the inverse Ackermann function, which grows extremely slowly and is effectively a small constant for all practical input sizes. If the nodes are not in the same component, the union function merges them. This operation involves a few constant time updates and a small number of find calls, yielding an amortized time complexity of O, alpha, n, per union. With n edges to process, the total time spent in this step becomes O, n asterisk alpha, n. Furthermore, if a cycle is detected during the union operation, the algorithm identifies the redundant edge instantly, without adding extra complexity, since the cycle check is integrated into the union logic. Combining these steps, the overall time complexity of the algorithm is determined by the initialization step, which takes O, n, and the edge processing step, which takes O, n asterisk alpha, n. As a result, the total time complexity is O, n asterisk alpha, n. Given the extremely slow growth of the inverse Ackermann function, this is effectively linear time for practical input sizes. Shifting to space complexity, the solution requires memory for the parent and rank arrays, each with n+1 elements. The parent array stores the parent node for each element, while the rank array tracks the approximate tree height for each component. Both arrays require O, n, space, as their size scales linearly with the number of nodes. In addition to the arrays, we must account for the recursive stack space used by the find function. In the worst case, the recursion depth corresponds to the height of the tree within the union find structure. However, thanks to path compression, the tree height is minimized, effectively becoming a constant, O, alpha, n. Consequently, the stack space required for recursion is negligible in practice, effectively O1. Combining all these factors, the total space complexity of the solution is O, n, which includes the space for the parent and rank arrays, with minimal additional overhead from the recursion stack. When comparing this optimized approach to a naive solution, the efficiency becomes clear. A brute force method might involve representing the graph as an adjacency list or matrix and performing a DFS or BFS for each edge to check if removing it disconnects the graph. Such an approach would require O, n squared, time in the worst case, as it involves traversing the graph repeatedly for each edge. Additionally, the space complexity would be O, n plus m, where m is the number of edges, to store the adjacency list. In contrast, the union find approach is far more efficient, reducing the time complexity to O, n asterisk alpha, n, and the space complexity to O, n. This makes the optimized solution highly scalable, even for large graphs with thousands of nodes. By achieving near linear time complexity and linear space complexity, the union find solution is a significant improvement over naive methods and demonstrates the power of efficient data structures in solving graph problems. When tackling this problem, there are a few common mistakes that can trip up candidates. First, failing to check edge cases is a frequent oversight. For instance, if the graph consists of only a single node or if removing an edge results in a disconnected graph, your solution might not handle these scenarios properly. It's crucial to verify that your code works for small inputs and unusual cases. Another common error arises during cycle detection, especially when using DFS or union find. For DFS, one mistake might be not skipping the parent node during traversal, which can lead to false positives for cycles. Similarly, mishandling parent relationships in union find can result in incorrect cycle detection. Efficiency is another area where mistakes often occur. A brute force approach, such as removing each edge and checking connectivity with a full DFS or BFS, can lead to an inefficient O, n asterisk, n1 runtime, which is impractical for large graphs. Lastly, misunderstanding the graph representation, such as assuming the graph is directed when it's actually undirected, or confusing adjacency lists with matrices, can lead to incorrect implementations. Always ensure you understand the input format thoroughly before beginning your solution. Another issue to watch out for is failing to restore the state in recursive solutions. For example, when using DFS or backtracking, if you forget to reset visited nodes or undo graph modifications after recursion, the state can become corrupted, impacting subsequent iterations. Now, let's discuss some interview insights for this problem. The concept of detecting cycles is a recurring pattern in graph problems. You should be comfortable implementing both DFS-based cycle detection and union find approaches, as these are commonly expected in interviews. Additionally, for tree-related problems, remember that a valid tree must have exactly n1 edges for n nodes and must be connected. Understanding these properties is essential. When comparing approaches, it's important to highlight trade-offs. While DFS-based solutions are often easier to understand and explain, union find is typically more efficient for larger graphs due to its ability to handle operations in nearly constant time with path compression. Lastly, always articulate the time and space complexity of your solution clearly. For instance, DFS has a time complexity of O, n plus e, where n is the number of nodes and e is the number of edges. Union find, with path compression, achieves nearly O1 time for each operation, which can be a significant advantage in certain scenarios. This problem is also closely related to several others, which you may encounter in interviews or while practicing. Examples include LeetCode 323, which involves finding the number of connected components in an undirected graph, LeetCode 261, which checks if a graph is a valid tree, and LeetCode 721, focusing on accounts merge. Understanding these problems can help you recognize recurring themes and strengthen your graph problem-solving skills. Now, let's consider alternative approaches to solving this problem. The union find approach is highly efficient for detecting cycles and maintaining connected components, especially when using path compression. However, it does require additional space for the parent and rank arrays, which is a trade-off to keep in mind. On the other hand, DFS or BFS approaches are often more intuitive and easier to implement, but they can be slower than union find for larger graphs due to repeated traversals. Another technique, topological sort, is useful for detecting cycles in directed acyclic graphs but is less relevant for undirected graphs like this one. Understanding when to use each approach and their trade-offs is key to demonstrating both efficiency and adaptability in solving graph problems. Great job! Today, we explored the redundant connection problem, discussing its solution using the union find algorithm. Remember, mastering efficient algorithms and data structures like union find is key to solving graph problems. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!